For half a century, the central processing unit was the undisputed king of computing. If you wanted a database to query faster, a software program to run smoother, or a video game to render at higher frame rates, you simply bought a chip with a higher CPU clock speed. The CPU was the ultimate general-purpose machine, but try to run a modern AI model on even the most advanced CPU, and the system grinds to a halt. AI workloads have pushed general-purpose silicon to a physical wall, triggering a silent, multi-billion-dollar revolution in how computer chips are designed, manufactured, and networked. But before we look at the architectures, what actually is a silicon chip? Silicon is a semiconductor, a material that can either conduct electricity or block it depending on how we control it. By purifying silicon and etching billions of microscopic switches called transistors onto it, we create an integrated circuit. When we organize these switches differently, we get completely different computing architectures. Today we are moving away from the one-chip-fits-all era. The hardware landscape is fracturing into specialized silicon, from RISC architectures like ARM and open-source RISC-V to parallel processing GPUs, hardwired ASICs like Google's TPU and Groq's LPU, and local NPUs built into our laptops. Let's start with the foundational division in CPU design, CISC versus RISC. Intel and AMD's dominant x86 architecture is built on CISC complex instruction set computing. CISC is like a Swiss Army knife. It has hundreds of complex instructions built directly into the hardware. A single instruction can tell the chip to load data, perform math, and write it back to memory. This makes assembly language compact, but it requires massive, power-hungry control units, branch predictors, and out-of-order execution logic on the chip to translate those complex commands into physical gate actions. But ARM has a massive competitor rising: RISC-V. RISC-V is an open-source instruction set architecture developed originally at UC Berkeley. Think of it as the Linux of microprocessors. Because it is royalty-free, any company can design, manufacture, and sell RISC-V chips without paying licensing fees. More importantly, RISC-V is modular. Designers can add custom extensions, like specialized vector math units for AI processing, directly to the silicon. This has made RISC-V the global standard for custom hardware accelerators, particularly as companies seek to bypass proprietary licensing and geopolitical export restrictions. But even the fastest RISC CPU is fundamentally sequential. It is designed to execute one task after another very, very quickly. This works perfectly for operating systems, browsers, and databases. But AI models are different. A neural network is essentially a collection of weights arranged in massive grids called matrices. To run an LLM, you must perform billions of simple matrix multiplications. A sequential CPU, even with multiple cores, becomes a massive bottleneck. You don't need a single genius processor solving complex logic puzzles. You need a massive army of basic calculators doing simple math all at once. This is why the industry turned to the graphics processing unit, or GPU. How did Nvidia capture this market? It wasn't just the hardware, it was the software. In 2006, Nvidia's CEO Jensen Huang made a massive bet. They launched CUDA, a parallel computing platform and programming model that allowed developers to write C++ code to run directly on the GPU. At the time, Wall Street criticized the move because it cost billions and reduced the hardware efficiency for video games. But when the deep learning boom hit in 2012, CUDA was the only mature platform available for training neural networks. Today, CUDA is Nvidia's ultimate monopoly. Every major AI framework, from PyTorch to TensorFlow, is optimized for CUDA, creating a software moat that is almost impossible for competitors to breach. But a GPU is still a general-purpose processor. It has to support graphics pipelines, physics engines, and various compute shaders. If you want to maximize speed and power efficiency, you strip out everything else and build an ASIC, an application-specific integrated circuit. This is silicon designed and hardwired for a single mathematical task. Google pioneered this in 2015 with the Tensor Processing Unit, or TPU. Google realized that if their users performed just 3 minutes of voice search daily using deep learning, Google would have to double its entire global data center footprint. To solve this, they built the TPU around a design called a systolic array. Instead of reading and writing to registers after every single multiplication, data flows through a grid of math cells like blood through a heart, passing intermediate results directly to neighboring cells. As AI models grow to hundreds of billions of parameters, compute speed is no longer the main bottleneck. The bottleneck is memory bandwidth. To feed thousands of compute cores, GPUs, high bandwidth memory, or HBM. HBM stacks memory dies vertically and connects them to the processor using an ultra-wide interface. But even HBM introduces latency because the data must travel across physical paths on the silicon substrate. The alternative is SRAM, static RAM. SRAM is built directly into the silicon logic gates, right next to the processing cores. It is orders of magnitude faster than HBM, but it has a catch. It is extremely expensive, power-hungry, and physically bulky, holding only a fraction of the data. This brings us to Groq's LPU, the language processing unit. Groq bypassed the memory bandwidth bottleneck by avoiding HBM entirely. Instead, they packed 220 megabytes of ultra-fast SRAM directly onto their LPU chip. Furthermore, they stripped out all dynamic scheduling hardware, no caches, no branch predictors, and no out-of-order execution logic. Groq's LPU is completely deterministic. The compiler determines exactly which instruction executes on which core at what exact nanosecond. The hardware does no thinking, the software plans the entire execution timeline. This allows Groq to achieve staggering token per second rates, though it requires chaining hundreds of chips together to hold a single large model. This speed was so threatening to Nvidia's dominance that in late 2025, Nvidia executed a brilliant antitrust dodging maneuver, a $20 billion strategic licensing agreement with Groq. In what analysts called a merger without the paperwork, Nvidia hired Groq's key engineering team, including founder Jonathan Ross, and licensed their LPU technology. Why? Because Nvidia is now building its own next-generation dedicated inference chip based on Groq's SRAM architectures, trying to lock down inference just like they locked down training. Why are companies doing this? Why not just buy more Nvidia H100s or Blackwell GPUs? It comes down to flexibility versus efficiency and pure economics. An Nvidia GPU is a general-purpose AI engine. It can train any model, run any architecture, and it utilizes CUDA, Nvidia's software monopoly. But these GPUs cost upwards of $30,000 each, and Nvidia is pocketing a 75% gross margin. If you are Meta, Google, or OpenAI running inference for hundreds of millions of users, that margin is a massive tax. You want custom chips tailored specifically for your inference workloads, stripping out everything you don't need to slash operating and energy costs. But tech giants don't build these chips alone. They partner with Broadcom, ticker AVGO. Broadcom is the toll booth of AI silicon. They don't sell branded AI chips. Instead, they provide the design platforms, advanced Ethernet networking, and manufacturing pipelines. They co-develop Google's TPUs, Meta's MTIA, and in June 2026, they co-developed OpenAI's first custom inference chip, codenamed Jalapeño. By outsourcing the packaging and networking to Broadcom, these firms can spin up custom silicon in a fraction of the time, directly challenging Nvidia's hardware monopoly. Specialization isn't just happening in massive cloud data centers. It is happening on the consumer edge. Modern laptop and mobile processors now feature built-in NPUs or neural processing units. Apple Silicon, Intel Core Ultra, and AMD Ryzen chips dedicate significant die area to these processors. An NPU is a tiny, highly efficient ASIC designed specifically to run low-precision matrix math for local AI features, such as on-device LLMs, real-time image processing, and voice recognition, measuring performance in TOPS without draining your battery. But as we push digital transistors to their physical limits, we face a fundamental architecture bottleneck, known as the von Neumann bottleneck, the massive amount of energy wasted simply moving data back and forth between memory and the processor. To solve this, researchers are turning to analog AI. In an analog chip, we store weights as physical electrical resistance in a component called a memristor. To multiply an input value by a weight, we apply a voltage to the memristor. According to Ohm's law, the current that flows out is the voltage multiplied by the conductance, doing the math instantly at the speed of physics. What does this silicon diversity mean for software developers? The days of treating hardware as a generic, abstract execution layer are officially over. If you write code today, the choice of compiler, framework, and target silicon will dictate your system's performance and cost. To navigate this, The industry is building cross-hardware software layers. For example, OpenAI's Triton language allows developers to compile code to both Nvidia and AMD chips without writing raw CUDA. Apple's MLX optimizes models for their unified memory. Understanding how to target these specialized chips is the next superpower. The era of the general-purpose CPU is over. The future of computing belongs to specialized silicon, where hardware and software are co-designed. As developers, builders, and creators, our job is to understand these physical architectures so we can build the next generation of software. Let me know in the comments which architecture you are building for, and I'll see you in the next video.